Hi, my name is Yu Zhang, and today I'm going to talk about the paper Plan Structured Deep Neural Network Models for Query Performance Prediction. My presentation will be divided into 5 parts. The first part is about paper summary, then I will talk about something related to the related work, and then is a part of evaluation. After that, I will talk about something about work critic. In the end, I will mention some suggested improvements. And okay, so what is this paper about? This paper is about using deep learning to solve the problem of query performance prediction in database management system. And research problem that the authors are trying to solve is the challenge of accurately predicting the latency of a query, which is difficult due to the complex interactions between query operators and improved relations that lack of natural adaptation to workload characteristics and query execution plan patterns. This paper have several interesting findings. Firstly, it shows that the proposed approach can be extended to incorporate cardinality estimation to improve the accuracy of latency prediction. And then the proposed neural networks eliminates the need for human feature engineering by automatically learning the interactions between operators and predicting the latency of query execution plans using operator-level neural units. This paper have several main contributions. Firstly, is operator. Firstly, it introduced the notion of operator-level neural unit. That is a deep neural network that models behavior or logical relation operators, and the neural units are designed to produce latency estimates and performance-related properties that might be useful for the latency prediction of the parent operator. And then it introduced the plan structured deep neural networks. This network can significantly designed to predict the latency of query execution plans by dynamically assembling operator-level neural units in a neural network architecture. And it also proposed optimizations for efficiently training the neural network, which decreased the model training time by nearly an order of magnitude. And it also presents the experimental results, which demonstrates the proposed approach can outperform the state-of-art techniques for query performance prediction. There are many works that related to this current paper. For example, the query performance prediction. Some work that focus on predicting multiple query resources usage metrics at the same time, but they didn't include execution times. And other work can predict statistics about queries in XML databases. The second topic is cardinality estimation. Cardinality estimation is related to query performance prediction, as an operator's cardinality often related to its latency. So various techniques have been proposed for cardinality estimation in robust static techniques, adaptive histograms, and deep learning. And work on query progress indicators involves frequently updating a prediction of query's latency. Various approaches have been proposed for this purpose, such as the estimate of latency of query as it is running. The estimate made at the state of query's execution may be inaccurate, but is quickly refined and corrected during the early stage of query progress. And for the deep learning part, it has seen a groundswell of activity in the system community. Various works has been applied in query optimization, entity matching, and index selection. So how this paper different from the previous work or have contributed to the community. Firstly, unlike previous work, the proposed deep learning architecture eliminates the need for human-crafted feature selection and automatically discover complex performance models both at the operator and query plan level. And it also utilized the weight sharing where the same neural unit is used for any instance of the same operator across plans, allowing it to learn complex interactions between operators. For the contribution, this paper proposed optimizations for effectively training the novel neural network architecture, which decreased model training time by nearly an order of magnitude. So, how did the paper evaluate a proposal? The paper evaluates the proposal by conducting experiments using TPCH and TPC-DS benchmarks. They executed 20,000 queries with a scale factor of 100 GB for each benchmark, and recorded execution times and execution plans using post-circle to explain analyze capability. The input features used for each neural unit were those that post-circle makes available through the explain command before a query is executed. The queries were split into a training side and a testing side in two different ways, and each neural unit had 5 hidden layers, each weighs 128 neurons. SGD was used to train the network with a learning rate of 0.001 and a momentum of 0.9. Training was conducted over 1,000 apples. The performance of proposed models were measured by comparing the result to state-of-the-art techniques for query performance predictions. Okay, so what is experimental method and techniques used in this research paper? The experimental method used in this paper involves comparing the proposed plan-based neural network model with 3 other latency prediction approaches, which are SVM, resource-based features, and tuned analytic model. Experiments were conducted using TPCH and TPC-DS benchmarks, and the performance of each model was measured using 2 metrics, which are relative prediction error and mean absolute prediction error. You can see that there is a figure that displays the result of comparison of the prediction accuracy for different methods. The accuracy of each method at estimating the latency of queries in the TPCH and TPC-DS workloads are shown in sub-figure A, and the results reveal that the neural network approach performance outperforms other baselines. For example, the relative error improved by 9% and 5% for TPC-DS and TPC-H separately over RBF. And in terms of absolute error, the average error decreased by 11 minutes and 7 minutes for TPC-DS and the TPC-H separately from RBF. For this part, I'm going to talk about the parts that I think that developed well and did not develop well. And okay, so for the part that I think developed well is that the authors of this paper have developed a novel neural network architecture designed to address the challenges of query performance prediction. They have present a clear motivation for their approach, describing the limitations of existing solutions and the benefits of their proposed method. The architecture itself is well defined and described in detail with a clear explanation of how it allows for plan-structured neural networks to be constructed by assembling operator-level neural units. The authors have also demonstrated the effectiveness of their approach through experimental results, showing that their model outperforms state-of-art solutions with manageable training overhead. But there are still some parts that I think did not develop well. For example, the paper doesn't discuss the choice of hyperparameters in depth. While the authors briefly mentioned the learning rate and the regularization strings, they do not provide a detailed justification for their choice. providing more insight into the hyperparameters selection process could help readers better understand how to apply the approach to new database. Um, besides, also mentioned that the cache size for the information sharing optimization that never exceeded 20 MB, but they do not provide any further details about how the cache was implemented or how the size was determined. And finally, the paper doesn't provide a detailed discussion of the limitations and potential weakness of the proposed approach. Uh, while the experiment result demonstrate the effectiveness of the approach on TPCH and TPC DS data size, it is unclear how well the approach would generalize to other data size. So I think a more detailed discussion of the limitations could be helpful to help the readers better understand its applicable understand its limitations. Okay, so for the part that I think could be implement differently is that it would be helpful if the authors provide more information on specific query workloads used in the experiments, such as number and complexity of queries, as well as any characteristics of data size used. While the authors do provide some insight into hyperparameter selection process, it would be, it would be helpful to display more details. And additionally, it may be useful to investigate the interpretability of the proposed model and to explore ways of explaining its predictions. As this could help database administrators and users understand the factors that contribute to query latency and potentially improve database performance. Finally, it may be valuable to investigate the scalability of the proposed approach and to explore ways of applying it to large-scale database with many queries and operators. So for the part that I think need additional justification is that it may be useful to provide more information on how the proposed model handle cases that there is a significant variation in query execution times. For example, in cloud environments where performance can vary based on a number of factors. The proposed optimization for reducing training overhead could be further explained and justified. Well, it is mentioned that these optimizations are effective. It will be useful to provide how they work and why they are appropriate for these tasks. In this part, I'm going to talk about the potential improvements. Firstly, one potential follow-up for this study could be evaluate the performance of proposed approach on a wider range of query workloads and data size. While the experiment result in the paper demonstrate that the proposed approach worked in on the TPCH and TPC-DS benchmark data size, it would be helpful to understand how well the approach generalized to other types of queries and data size. And besides, it would be helpful to investigate the potential impact of the performance fluctuations on the accuracy of the model. Experiment results in the paper were based on query executed on a environmental survey, but a cloud environment performance can vary based on the time of day or other factors. So investigate how the proposed approach performs under different performance conditions could help provide insights into its applicability in practical settings. And here are some new ideas that I want to explore. Firstly, is the use of a proposed approach for predicting the performance of concurrent queries. This could involve exploring how the neural network architecture can be adapted to handle resource usage requirements and computation for resources between multiple queries. And secondly, I want to investigate techniques for improving the training time for of the neural network, such as using a different optimizer or taking advantage of transfer learning techniques. This could involve experiments with different optimization algorithms or pre-training the model on a larger data size before fine-tuning on the target data set. And for the last part, I think there are many ways that we can apply this approach to real-world applications. First is about query optimization. The proposed approach can be used to predict the performance of different query plans, which can help database administrators select the most efficient plan for a given query. And this can lead to faster query processing times and improve system performance. And we can also use it for capacity planning. By accurately predicting the performance of queries, the approach can be used to estimate the amount of resources like CPU, memory, and disk, which are required to support a given workload. And the information can be used to perform capacity planning and ensure that the database system has sufficient resources to support the workload. And we can also use it for performing tuning. The approach can be used to identify queries that are causing performance bottlenecks and optimize the database system to improve their performance. This can involve adjusting database configuration parameters and adding indexes to tables or other performance tuning techniques. So I think that's all for my presentation today, and thank you for your hearing. Bye bye.